The Beirut port explosion was a searing testament to the catastrophic consequences of ignored warnings and systemic negligence. While ammonium nitrate detonated a city, another kind of dormant danger lies beneath our feet, waiting for a single miscalculation to unleash chaos. Our journey takes us deep underground, to a disaster that, though less visible, offers equally profound lessons in the perils of oversight. This is the story of the Quecreek Mine, where a failure of geotechnical mapping plunged an entire operation into an urgent, desperate fight for survival. In July 2002, in Somerset County, Pennsylvania, the Quecreek Mine was a vital part of the region's coal industry. It was a modern operation, employing skilled miners who worked tirelessly, extracting coal from deep seams. Every shift carried inherent risks, but the industry relied on meticulous planning and geological surveys to mitigate these dangers. Miners trusted the maps, believing they outlined safe zones and clear boundaries. This trust, however, was about to be profoundly betrayed, not by a sudden collapse, but by an unseen, historical oversight. Deep earth engineering, particularly in mining, hinges on the accuracy of geotechnical mapping. These aren't just simple drawings, they are complex interpretations of subsurface geology, outlining rock strata, fault lines, and crucially, the locations of old, abandoned workings. These maps dictate where miners can safely extract resources, ensuring they don't unwittingly breach unstable ground or, even worse, dormant hazards. A precise, verified map is the miner's most critical safety tool, a safeguard against the unseen forces of the earth. The Quecreek disaster stemmed from a critical oversight, the reliance on outdated survey data. Decades earlier, neighboring mines had ceased operation, and their final survey maps, crucial for current operations, contained significant inaccuracies. These old maps, some dating back to the 1960s, depicted an adjacent, abandoned mine's boundaries incorrectly. Despite advances in survey technology, these historical documents, lacking modern verification, were integrated into the contemporary mining plan, laying a silent, hidden trap for the Quecreek miners. Unknown to the Quecreek miners, barely 60 feet away from their active workings lay the abandoned Saxman Mine. This old mine, having been active since the late 19th century, was completely filled with water, millions of gallons trapped behind crumbling rock and forgotten passages. Its exact location, depth, and extent were inaccurately represented on the inherited maps. This vast, subterranean reservoir posed an existential threat, an immense hydraulic pressure waiting for the slightest breach to escape. The miners operated under the assumption that a protective barrier of coal, approximately 200 feet thick, separated their workings from the old, flooded Saxman Mine. This crucial safety margin was based entirely on the flawed historical surveys. Their plan was to extract coal up to this perceived barrier, ensuring a safe distance from any potential water hazard. But the reality underground was drastically different, a spatial discrepancy that would soon turn a routine mining day into an emergency. On July 24, 2002, at approximately 9 p.m., the sound of a drilling machine echoing through the mine changed abruptly. Miners had advanced into a coal seam, nearing what they believed was a safe distance from the abandoned mine. But the outdated maps had misled them. With a sudden, terrifying rush, the drill bit punched through the last few feet of rock into the Saxman Mine. The protective barrier was not 200 feet, but a mere few yards, breached in an instant. Millions of gallons of frigid, black water from the Saxman Mine immediately began to inundate the Quecreek workings. The water, under immense hydrostatic pressure, surged through the newly formed opening, rapidly filling the tunnels. Within minutes, the main passageways were submerged, cutting off escape routes and trapping 9 miners deep inside the earth. The sound was deafening, the darkness absolute, as the mine transformed into a deadly, submerged labyrinth. 9 miners found themselves stranded, their escape routes swiftly consumed by the rising floodwaters. They managed to gather in a small, elevated pocket of the mine, a desperate sanctuary. With limited supplies and no communication with the surface, their situation was dire. The frigid water threatened hypothermia, and the air quality, while initially breathable, was a constant concern. Above ground, news of the disaster spread, igniting a frantic, multi-agency rescue effort. The immediate challenge for rescue teams was locating the trapped miners and understanding the complex hydrology of the flooded tunnels. Time was critical. Engineers and experts from various fields converged, their first task to accurately map the mine's new, water-altered landscape. This wasn't just about finding people, it was about precision engineering under extreme pressure, a desperate race against the rising water and dwindling air, all while operating on limited, and previously flawed, information. Understanding the precise hydrology of the flooded tunnels was paramount. Rescue engineers needed to determine the rate of water influx, the remaining air pockets, and the best points for drainage and rescue shaft drilling. This required real-time data collection, utilizing sonar and advanced geophysical surveys to penetrate the earth and map the submerged passages. The flow dynamics, water levels, and even temperature had to be constantly monitored to make informed, life-saving decisions. The rescue centered on drilling multiple shafts from the surface. First, smaller boreholes were drilled to provide air and communicate with the trapped miners. Then, the most critical step, a larger rescue shaft, wide enough to extract the miners, had to be drilled with pinpoint accuracy. This required advanced GPS and laser guidance systems, ensuring the drill bit hit a specific, tiny target hundreds of feet below ground, avoiding any further structural damage or water breaches. In a cruel irony, the disaster necessitated immediate, intensive geotechnical remapping. While outdated maps had caused the calamity, accurate, real-time mapping became the key to salvation. Surveyors worked tirelessly, using modern techniques to create precise, three-dimensional models of the mine, identifying the miner's exact location and planning the rescue shafts. This rapid re-evaluation of the subsurface, discarding old errors, was fundamental to the success of the complex operation. For 77 agonizing hours, the world watched. The rescue operation was a relentless battle against time, water, and earth. Teams worked non-stop, drilling through hard rock, pumping out millions of gallons of water, and maintaining communication with the trapped miners. Every decision was critical, every measurement double-checked. The entire effort was a testament to human resilience and the collaborative power of engineering and emergency response, all focused on the singular goal of reaching those trapped below. Finally, after more than 3 days, the rescue capsule reached its target. One by one, the 9 miners were brought to the surface, emaciated and weakened, but alive. The moment was met with jubilant cheers and widespread relief. It was a miracle of modern engineering and human determination, but it was also a stark reminder of how close they came to succumbing to a disaster that was entirely preventable. The sight of each miner emerging underscored the profound impact of robust safety protocols. The Quecreek disaster led to extensive investigations. The primary culprit was clear: the failure to verify outdated survey data. It highlighted a critical flaw in industry practices, a blind reliance on historical documents without sufficient modern due diligence. Investigators scrutinized every step, from the initial geological assessments to the final operational plans, concluding that a lack of rigorous data verification protocols was the root cause of the catastrophic breach. In the wake of Quecreek, the mining industry implemented stricter safety protocols. Emphasizing rigorous data verification became paramount. Modern technologies like LiDAR, advanced radar, and 3D geological modeling became standard, ensuring that historical maps were either resurveyed or deemed unreliable. Protocols were established for mandatory pre-mining boreholes to probe for unknown water hazards, transforming the approach to deep earth engineering and preventing future such incidents. The Quecreek Mine disaster, much like the Beirut blast, stands as a powerful, albeit somber, case study in the profound impact of negligence. It underscores the critical necessity of rigorous data verification, not just in mining, but in all forms of deep earth engineering. The 77-hour rescue showcased human ingenuity and bravery, but the event itself was a stark warning: the Earth holds many secrets, and our maps must be truthful, constantly updated, and meticulously verified to ensure the safety of those who venture beneath the surface.